Okay, good morning. Good morning. Okay, let us start. So today's lecture, heterocyclic compounds and nucleic acid. It's a brief information about some the most important compounds, biochemically important compounds consist exact nature rings. If you remember the classification of all organic compounds according to the structure of carbon chain can be due to the is it cyclic or aliphatic. So cyclic compounds themselves, they can be classified into two groups. Are they homo or heterocyclic? Homocyclic to be, they're supposed to be only carbons in a ring. Functional groups, any substituents around being bonded to the carbon chain in a ring, not effect is it homo or heterocyclic. But if there at least one heteroatom present, these compounds are known as heterocyclic. So, heterocyclic compounds are organic compounds containing a ring made up of more than one kind of atom. Due to what atom is there, we can classify the heterocyclic compound into a few groups. Classification here is well important as for aliphatic, because of huge number of heterocyclic compounds can be found in nature, and they are too different in their chemical and biochemical behavior. That's why classification is so important. There are four types of classification. First one, according to the size of the cycle. The simplest three-membered rings, but they are not often can be found in nature. Four as well, but 5 and 6 membered, they are quite often can be found in nature. 7-membered rings also can be found, but not in biochemically important compounds. So second classification according to the nature of heteroatom. Heteroatom can be oxygen, can be nitrogen, can be sulfur. The most often can be compounds consist more than one. That means oxygen and nitrogen containing, sulfur and nitrogen containing. Not often, but can be compounds consist more than 3. Third type of classification, it's according to the saturation degree. This classification is the same as for homocyclic. So all cyclic compound and heterocyclic also can be classified as saturated, unsaturated and aromatic. How to prove is it aromatic or not? You should know it's according to Haeckel's rule. I will remind you then. And last one but not least, it's a classification according to the number of cycles. They can be mono, consist only one ring, and polycyclic. From all polycyclic, the most important and more often can be found in nature, condensed cycle. And now let us take the most important from biochemical and medical point of view heterocyclic compound to see their structure and some examples where they can be found. From 5-membered rings, the most important, they are aromatic, pyrrole, furan, and thiophene. These 3 heterocyclic compounds consist one heteroatom, nitrogen, oxygen, or sulfur, and they are aromatic according to their nature, according to the structure, according to the saturation degree. Why they are aromatic? I want to remind you how to prove this. To be aromatic, compound should has coplanar structure, being completely conjugated. That means all atoms of the rings should participate in this extra overlapping with formation of delocalized pi bond. And the last but not least, it's a Haeckel formula. For n plus 2, it's equal to the number of electrons in this delocalized pi bond. It's supposed to give us number with integer n finally. So let us check these cyclic compounds. In all of them, they are all carbons sp2 hybridized. In every and each sp2 hybridized carbon, and total number of atoms in the ring, 5. So that's why they are coplanar cyclic, planar structure, plate-like structure. P pi are conjugated each. As in conjugation, takes part heteroatom with lone pair. Nitrogen single bonded lone pair donor, oxygen, sulfur as well. So for n plus 2 as a result, so conjugation p pi and number of electrons in this delocalized pi bond will be equal to 6, as the nitrogen, oxygen, sulfur, lone pair donors in this case. So n is 1. These rings even more concentrated according to electron density as benzene. Why? Because of there was 6 electron delocalized and belong same moment to 6 carbon atoms. Here 5, but number of electrons 6. More concentrated ring. But it's not perfectly delocalized as nitrogen, oxygen, and sulfur heteroatom with higher electronegativity than carbon, and that's why they attract electron density, make this compound be active in some unique nature chemical reactions. So how to name any derivative of such compound if they have no common name? We need to number properly the atoms in this ring. And here we have priority order for heterocyclic compounds. Heteroatom higher in priority than any functional group, even carboxylic. So that's why we start numbering atoms in a ring from heteroatom, and then we can move anti-clockwise. Important to number such way the substituent or the highest functional group, if it's present, has a smaller number as possible, but number 1, it's a heteroatom number. So let us practice with one example. For example, such derivative of pyrrole. So what we know, to name this compound, first of all, we need to check, do we have here any functional group or not? We don't have. Here just alkyl group, they can be in prefix part only. So what about numbering? Nitrogen as a heteroatom should be numbered first. And then we will look clockwise for substituents as a smaller number as possible. It starts earlier. That's why we move such way. It says 3-ethyl. As you remember, we number prefix part according to alphabetical order. 3-ethyl, 2-methylpyrrole. So this is a way to name such compound. We have other type of naming. It's for such compounds symmetrical nature. Second and fifth can be numbered as an alpha, third, fourth as a beta. But when there are two different substituents, such numbering is unacceptable. So there are some examples of such 5-membered ring compounds, and one of them is a heme. It's a structural unit of hemoglobin. It's a protein. 4 subunits consist, each one with such part, and that's why such proteins like hemoglobin, they're known as chromoproteins, they're red pigment. So what we see here, that pyrrole here bonded with other pyrrole forming tetrapyrrole nitrogenous base. It's a ligand, bioorganic, important organic ligand. So such type of ligand, tetrapyrrole nitrogenous base, is known as porphyrin. So here, as you see, 4 bonds to the iron. Iron 2 positive, definitely. Due to different substituents here and due to the nature of the heteroatom, such tetrapyrrole nitrogenous base can be present in other biochemically important compounds like vitamin B12, for example. In plants we can find chlorophyll, no, and so on. Some enzymes also consist similar. So furan present in nature quite not often, let us say so. So what we know, we saw already compounds, some students who pass the topic carbohydrate. We know that furan derivative, completely saturated with hetero functional nature compound, that's mean polyol there. So such compound present in cyclic nature carbohydrates, known as furanosic cycle. For example, fructose cyclic compound, its furanosic cycle consists mainly, as well as ribose, ribofuranose, fructofuranose. There furan is present, but not furan itself, a completely saturated one with a OH group bonded to the ring. Nitrofuran found some application in medicine as antiseptic and antibiotic, antiseptic, furacilin or furacilinum, furadanin, and not often used for now, it's furazolidone. As you see, they consist nitro, alpha nitro, furan. And thiophene also not found too often, derivative of the thiophene present in vitamin H, biotin. So all vitamins biochemically important, and this vitamin, one of the function is responsible, as you see, it's a source of sulfur, a sulfur essential component, participate in collagen synthesis. Also vitamin H responsible for metabolism of glucose somehow and fat metabolism. So this is what about 5-membered ring with 1 heteroatom. But there we have such 5-membered rings with 2 heteroatoms. Can be more, but these are the most important. So pyrazole, imidazole, thiazole, and oxazole. These 4 the most often used and found in nature as well. So pyrazole, take a look, consists 2 nitrogen as well as imidazole, 2 nitrogen, but they are different according to the nature of bonds they are bonded in our ring. So what we see, such nitrogen where 3 sigma bonds and 1 non-hybrid with lone pair, this is electron pair donor, participate when it participates in a conjugation. So such nitrogen known as pyrrole nitrogen atom from the previous. Such nitrogen, it's a double bonded nitrogen, will be present in a compound I will show you soon. This is 6-membered ring, pyridine. So take a look. According to priority order, when we deal with a few heteroatoms, oxygen, it's the highest one in priority order, then sulfur after, then pyrrole nitrogen atom, and the last, according to priority order for numbering, it's a pyridine nitrogen atom. So that's why when we number, we start with the highest according to priority heteroatom. Again, heteroatoms more important for numbering as any functional group. So we start numbering from the highest, that means from pyrrole nitrogen atom, and then we can't choose now. We will move such way second heteroatom as smaller number as possible. So that's why we have here in this case anti-clockwise. For imidazole, same 1,3 position. For thiazole, sulfur higher, that's why 1,3 position. And oxazole, 1,3 position. All of these compounds, they have IUPAC names, IUPAC names, but they are quite hard to name all of these compounds because of even secondary suffix depends on saturation degree. There are a great number of different heterocyclic compounds, their names, and not necessary for from biochemical point of view to memorize all of them. You're not chemists. So let us see where these compounds can be found. But before, I will remind you how to name. So what here we can see? Substituents, not same, not important. That's why again we number such way the highest functional number, heteroatom number 1, and next one number 3 in this case. So that's why 5-methyl imidazole. So what about derivatives? No, analginum everyone knows, anti-inflammatory, anti-pyretic, and some other functions we applied, but pyrazole not often. Seldom even can be found in nature. But imidazole much more often, and one of the important, essential even compounds we deal with when we name imidazole, it's a histidine. Essential amino acid can't be synthesized in our body, takes part in huge number of biochemically important reactions, and due to decarboxylation process, it formed biochemically important substance we know as histamine. Everyone who ever suffered because of allergy known that all reactions we suffer, they appears because of histamine releasing, and even antihistamine drugs, as you know, we applied in this case. No, so not only there are a huge number of effects it produces, it's very biochemically active one. So we will discuss class time more exact. So thiazole, it's a structural unit of some antibiotics, for example penicillins. Together it's a condensed cycle, as you see, condense. Among 6-membered rings, they are nitrogen containing and one of oxygen containing, you already know, it's a gamma pyran or alpha pyran. It's a structural unit, completely saturated structural unit of carbohydrates as well as 5-membered, as you remember, glucose. Glucopyranose, pyranosic structural unit. So about nitrogen containing, it's pyridine and pyrimidine. Pyridine or pyridine, I heard both. So pyridine, it's a heterocyclic compound with 1 nitrogen. When we number, definitely we start numbering from this nitrogen, and then here, as you see, we can move anti-clockwise due to the where substituents are. And here it's also symmetrical, that's why it can be alpha, beta, and here also present gamma position, the 4th one. For pyrimidine, there are 2 nitrogen, 1-3 positions, they are absolutely same according to the priority order. So according to the kind of tradition, we start numbering from the lowest, but it doesn't mean that we can't start numbering from the 3rd one, numbering first, and move then clockwise, but 1-3 position. Such nitrogen atom, as I told you just before, even has such name, pyridine nitrogen atom. It's a double bonded one. Some examples for pyridine, it's a vitamin PP, nicotinamide, prevent pellagra, that's why it's clear, deficiency leads to pellagra, and vitamin B6. What about condensed cycle? There are a huge number of them possible to find, but the most common indole and purine. So what about them? For indole, their numbering is a IUPAC way. We number IUPAC way. They are the one only nitrogen here, heteroatom pyrrole nitrogen atom, and that's why we start numbering from it. Then we number 5-membered ring. That means we move anti-clock 1, 2, 3, and we need to continue same direction. But here we never number atoms belongs to both cycles same moment. Why so? There are no hydrogen to be substituted. But we number such way to show where substituent can be. So that's why there are 7 numbers, but really 9 carbons. So this is indole. And purine, it has common numbering because of its biochemically important substance, structural unit of some nitrogenous bases. That's why nucleic acids structural unit. It was numbered before IUPAC system. So that's why necessary to memorize, unfortunately for you, where the number 1. The highest priority order, nitrogen, pyrrole nitrogen, will have the last number. So it's necessary to memorize that first one is here. And that's what then we number such way the second heteroatom should be the smallest number as possible. So that's why we move anti-clock, and according to this common way to number, we number all atoms, and 6-membered we number first. So take a look, there are 6 will be 6 atoms, and we already numbered their atoms belongs to both cycles same moment in condensed way. So they have 4th and 5th place. That's why 5-membered ring we should continue same direction. That means clockwise. 6-membered anti-clock in our case, and 5-membered clockwise. And 4, 5, 6, 7, 8, 9, as 6 already present in 6-membered ring. And again, as the highest in priority pyrrole nitrogen atom has number 9. This is very important because of then in nucleic acid, this compound will form a unique nature bond and 9 glycosidic. So what we have as example here for indole, except LSD, we can find this compound in one of amino acid also participate in formation of proteins, but also play some important role in huge number of biochemical reaction. And one of them is a formation of serotonin. It's a neurotransmitter. So, and let us start with the derivatives of purine, and not only purine, it's a nucleic acids. So as I hope you know that nucleic acids, DNA and RNA, you should know this, they are even secondary structure, how it look like from biology course, from school even. But let us see how they look like from chemical and biochemical point of view. So nucleic acids are polymeric compounds. They are lone polymers with a molecular mass much higher than 5,000. We know that polymeric compound, higher molecular weight compounds, all of them with a higher than 5,000. But here 25,000 and higher. 1 million, it's normal to have such a molecular weight. So according to their structure, they are polynucleotides. There are 2 types of nucleic acids, RNA and DNA, ribonucleic acid and deoxyribonucleic acid, and they have different biochemical important, as I hope you know, that DNA is a source of genetic information, and RNA participate in a protein synthesis. So let us see how these structures looks like. To understand and finally to draw dinucleoside as a structural unit of DNA RNA, what you should know how to draw in this course, and this kind of question present in your last checkpoint number 4. So not all nucleic acid, but a short unit of it, dinucleotide. To draw it is necessary to understand what structural unit and what kind of bonds bond them together. So how to understand polymeric compound structural composition? Necessary to use hydrolysis. And hydrolysis for nucleic acid proceed step by step, even with a change of the medium and in our body because of different enzymes present. So nucleic acid, first step of hydrolysis, destroyed the bond between monomers to form a mixture of different nucleotides. Nucleotides are made by nucleosides and phosphoric acid. What way they are bonded, I will show you that. And nucleosides themselves, they are also consist two units bonded with exact nature bond. They consist nitrogenous bases, different nature, and sugar. Due to the nature of sugar, they all can be classified as DNA and RNA. So let us start with the structural units. Phosphoric acid, I hope you remember what kind of nitrogenous bases there can be. In DNA and RNA, they are derivatives of pyrimidine and purine. How to number these rings, I just explained a few minutes above, and that's why where the functional groups and substituents present there, we can indicate with exact nature locant. So there are three pyrimidine nitrogenous bases. Four nitrogenous bases consist OH group bonded to the benzene ring. No, here not benzene ring, they are heterocyclic aromatic ring. They are possible to find unique type of isomerism, we know is tautomerism. I will show you then, but for now necessary to memorize that only lactam forms present in nitrogenous base, which are structural components of DNA RNA. Only lactam form. So there are three nitrogenous bases can be structural units, major structural units of nitrogenous bases DNA RNA. Can be minor nitrogenous bases, but not often, and in exact nature DNA RNA. RNA more often consist minor nitrogenous bases, but DNA not often. So uracil, for short ura, thymine, it's a THY. As you see, similar structure, but fifth position methyl group. And cytosine, CYT for shorter, it consists amino group and oxo group as well as all other. Important, see, second position, all of them consist keto group, oxo group, it's not exact keto, oxo group, and for first nitrogen atom being pyrrole nature. Why? Because of that first nitrogen atom participate in the formation of bond with the sugar. And two types of purine nitrogenous bases, only one of them in a lactam form, guanine, GUR for shorter. For adenine, lactam tautomerism, not typical, impossible, because of there no OH group. It's amino, 6 amino purine. So, as you remember, I hope just some number of minutes ago, I numbered purine, and it's a common numbering. I remind you that ninth one, the highest in priority order, nitrogen in purine cycle, it's a number 9, and it's pyrrole to participate in formation of bond with the sugar. So lactam tautomerism. I want to remind you that tautomerism, it's a kind of isomerism when both isomers, structural isomers, in equilibrium with each other. In our body, tautomerism, so this equilibrium between these two forms, shifts to the lactam form. They are both are uracil. So what is lactam form of uracil? It's 2,4. Remember 1, 2, 3, 4. 2,4 dihydroxy pyrimidine. When OH group bonded to the sp2 hybridized atom, it's kind of structural cyclic enol, as you remember, they are in equilibrium with the hydrogen moved to the nitrogen. So hydrogen moved to the nitrogen, double bond moved to the oxygen. This is lactam-lactam tautomerism. For uracil, there were 2 OH group, that's why 2 oxo group finally formed. For thymine situation is same, just CH3 group different. Guanine from pyrrole nitrogenous bases. Here, second position, amino group, nothing happened to due to this type of isomerism. And 6th position OH group in equilibrium with a lactam form. Again, only lactam formed present in DNA RNA. If there somehow equilibrium shifts backward to lactam, it's a mutation. And primary, mostly secondary structure of DNA can't be formed. It's a mutation. So, RNA, DNA, different in composition in one nitrogenous base. Both of them consist cytosine, adenine, guanine, but RNA, the major structural unit in nitrogenous base is uracil, for DNA, thymine. So different in these compounds, as you know, as I told you, CH3 group present in the 5th position. Sugar also different. So some students already passed this topic, that's why I should know that carbohydrates can be found in cyclic and open Fischer structure. Open cyclic, the equilibria. Mostly they are 99% present in cyclic form, and but in aqueous solution there can be found less than 1% of open Fischer structure. Definitely in DNA RNA only cyclic structure present. So this is furanosic cycle of ribose. For RNA it's just beta ribose, but from chemical point of view, correct to name it beta D minus ribofuranose. Here I didn't mention minus, it's just a dash. Minus plus because of optical activity. Ribose, it's a lever rotatory, it's rotate negative angle. So D minus but L plus. So beta D minus ribofuranose. To name it beta ribose, in biochemistry acceptable, but in chemistry not, because of ribose is 5-membered twin here, but can be possible to find 6. Very small percentage, but can be. So that's why necessary in chemistry indicate both in position and nature of the ring. How to number this structure? It's the same as we numbered carbohydrates. So we start numbering from the OH group, which formed due to formation of the ring after aldehyde group adds to the hydroxy group, second last. And why here with apostrophes? Because of when this sugar combine with the nitrogenous base, they becomes one structure but isolated from each other. That's why they should be numbered independent way. According to the tradition, nitrogenous base we number just without any apostrophes, and sugar, to show that their then substituents will be present bonded to the sugar but not to the nitrogenous base, we use apostrophes. 1, 2, 3, 4, 5. For DNA structural unit, it's a 2-deoxy beta D minus ribofuranose. Second position, OH group is absent. There, CH2. But everything else same. Now, when nitrogenous base combine with the sugar, let us start with RNA structural unit. What there happen? In sugars, in disaccharides and polysaccharides, there already was found glycosidic bond. But there it was alpha or beta oxygen, and then it was necessary to indicate is it 1, 2, 1, 4, 1, 6 glycosidic bond, because of there was possible to find how it's bonded, alpha or beta oxygen OH group. Then there was possible to bond different carbon atoms So that's why it was long indication of the glycosidic bond. Here also glycosidic, but carbon from the sugar ring bonded to the nitrogen in our nitrogenous base. In all cases, there will be carbon-nitrogen bond, carbon first position in all cases. So that's why we shouldn't indicate that it's a 1-1 apostrophes. We need to indicate just nitrogen number because of different nitrogenous bases. There are purine also present in DNA RNA, and that's why there will be a N9 glycosidic bond. So sugar bonded because of beta OH group was. That's why in all cases, doesn't matter what is a structure, what is nucleoside, there will be beta bond. No, that's why enough to indicate is it N, that it's N, and 1. In some nitrogenous bases, they are found different carbon can be bonded to carbon, but it's a minor nitrogenous basis. So, how to name? Uracil with ribose. So for such nitrogenous bases, when we deal with pyrimidine nitrogenous bases, suffix idine. So uridine. For shorter, just U. Cytosine with ribose, cytidine. This is our RNA structural unit. Suffix idine. Uridine, cytidine. And one glycosidic bond bonded sugar with a nitrogenous base. When we deal with purine nitrogenous base, adenine and guanine consist. For RNA, there will be similar nature bond, but it will be bonded to 9th nitrogen in purine nitrogenous base. So this is adenine. For guanine, similar structure here, but second position will be oxo group, amino group, 6th position oxo group. So adenosine, necessary to memorize. So for purine nitrogenous bases, suffix ozine when it's bonded to the sugar. So adenine with ribose, adenosine, and guanine with ribose, guanosine. A or G for short. This is RNA structural unit. For DNA structural unit, there will be similar structure with exception. Second position, there are no OH group, but just hydrogen, and one nitrogenous base different, not uracil but thymine there. Suffix is same, idine for pyrimidine nitrogenous bases. Here necessary to memorize that when we deal with such nucleosides, and it's a DNA structural unit, to show that it's cytidine or deoxycytidine, we add D as a prefix, deoxy, and D as a short. So can be cytidine or deoxycytidine, DC or C, but for thymine as its structural component of DNA, not necessary to add prefix deoxy. It's thymidine just. And when we hear this name, when it's written, we understand it's a structural component of DNA because of thymine is there as a major nitrogenous base. For shorter DT still, because of its a structural unit of polymeric compound and polymeric position and order of this nucleotide unit there, we indicate using short, and that's why DT there will be in a line. For shorter DT, but the name thymidine. And one glycosidic bond, same nature as in RNA. And for DNA, purine nitrogenous bases, so bond same way as in RNA nucleosides. The suffix ozine still, the prefix deoxy. Now here supposed to be DA. DA, deoxyadenosine. Deoxyguanosine, DG, DA, N9 glycosidic bond. What is nucleotide? So nucleosides consist nitrogenous base and sugar bonded and glycosidic bond, N1 or N9. Nucleotides consists nucleoside bonded with a phosphoric acid. Where this bond can be? It can be fifth position bonded to the sugar or third position bonded to the sugar. This is fifth position bonded. What way? Ester bond, OH group of the sugar. It's alcohol group, we can say. Esterification way bonded to the phosphoric acid. It's not directly happen. It's a biochemical process, formation of nucleotide. But the idea is still same. Ester bond. So how to name such compound? No, one of the questions you should be able to solve, necessary to draw nucleoside exact way named and indicate all bonds there. So we indicate bonds between nitrogenous base and sugar, same as we just did. It's N9 glycosidic bond when we deal with purine nitrogenous base, and ester bond between phosphoric acid and sugar. How to name? We should name the nucleoside with no change in the suffix. Why? Because of suffix will depend on the main functional groups here. Here the same structure, just fifth position OH group bonded to the phosphoric acid. The main functional group is phosphoric acid. No, not main function, main structure. It's an ester of acid, and that's why here it's a prefix. Prefix with the same suffix because of there are no change in a major functional groups. They are bonded. So adenosine, then we indicate where this ester bond is. It's a fifth position carbon bonded to. And monophosphate, or just phosphate for short. Why better to indicate monophosphate? Because of then short will be AMP. Fifth position, 5 apostrophes. Why it's important to indicate it here? Because of can be thought. Can be thought. Same name, AMP for shorter. Still adenosine monophosphate, but third position ester bond. Such compounds, they can be accepted as derivatives of acid still. It's still acid because of still form ester bond and still can form salts of such acid. So that's why their adenylic acid can be named as well. Adenylic acid or adenosine monophosphate. So guanylic, adenylic acid, so that's why there's supposed to be no problems with the adding suffix. That's why salts of such compounds will be adenylate because of adenylic acid, adenylate. Sodium, for example, adenylate. In nature, and they participate in biochemical, some huge number of biochemical important functions. It's a cyclophosphates. As you see, one phosphate group, ester bonds, 2 ester bonds. They're different ester bonds, not phosphodiester. Then we will see how it looks like. 2 ester bonds bonded to the same sugar, both third and fifth position. It's a cyclophosphate. 3,5 cyclophosphate. Important because of diaphosphates can be cyclophosphates. They are same phosphate bonded twice. Diaphosphate can be when 2 different phosphates groups, and can be diphosphate when we deal with ADP. They are 2 phosphate groups but bonded once through from the one of the diphosphate bonds, are not 2 phosphates. So ATP structure I will show you then. So what is the structure of nucleic acid? For shorter, I took trinucleotide, but it's a polymeric, as I told you, with a very, very long chain. So what here we see? The order of polymeric unit here of monomers from 5th end to 3rd end. That's why when we name, we start naming from 5th position. We never name these nucleosides. We indicate they're short. As its structural unit, as you see, of DNA, deoxyribofuranose. We can write DA, DC, DG, or D can be written once before bracket, and ACG if it's from the central part. That's why it can be continued left and right, upper and lower. If it's just trinucleotide, there will be no symbol means continued. So take a look how these nucleotides bonded to each other. They are bonded with a unique type of bond, knowing phosphodiester bond. 2 ester bonds, but 1 phosphoric acid unit. Phosphodiester bond. And nitrogenous bases bonded to the sugar such way all nitrogenous bases looks to the next chain. They are right side from. They looks to the next chain, will be opposite direction. And no, it seems like mirror image to it. And not exactly, but seems like. So it should be written such way our functional groups looks to the next chain. It's an anti-structure. So this is polynucleotide chain part from 5th to 3rd. That means primary structure of DNA, it's a polynucleotide chain. If you ask to explain how it's stabilized by phosphodiester bonds. What is the secondary structure of DNA? It's a double helix. So there are 2 chains, opposite direction, from 5 to 3 first chain, and from 3 to 5 second chain. Our nitrogenous bases, all of them aromatic, that's why looks planar, they are planar structure. And it's same plate, they are bonded hydrogen bond to the second chain, like mirror image look like polynucleotide chain. The number of bonds, hydrogen bonds between nitrogenous bases, it's strictly written, or 3 or 2, and we will see how these bonds are formed and how this means secondary structure of DNA is stabilized. So more complete explanation of complementary principle you will get and you will deal with next year in biochemistry. Now we will see how these bonds look like from chemical point of view. So there are 2 types of nitrogenous, we say pairs, complementary pairs, or base pairs for short. Thymine, adenine, guanine, cytosine. They are stabilizing secondary structure of nucleic acids. What way? As you remember, hydrogen bond, it's a very weak bond, maximum 20 kilojoule, from 8 to 20 kilojoule per mole energy, and they are no overlapping. But at present, it forms between hydrogen and more electronegative atom. It can be intermolecular, here intramolecular. So one chain, so it's not a just thymidine, it's not just, it's a part of polynucleotide chain. That's why I indicated here that it's already bonded. It's not a free nitrogenous base, it's a part of the chain. It's bonded to the sugar, that means strict, it fixed in exact point, in exact part of first polynucleotide chain. Second one, opposite direction, that's why sugar here, polynucleotide chain here, from 5th to 3rd. And our nitrogenous bases in one line, or they have one plate, both of them aromatic, and they should be in the same line, same plate, to be able to form hydrogen bond. Here, between thymine and adenine, 2 hydrogen bonds. Between hydrogen and nitrogen, and between oxygen and hydrogen. Hydrogen, oxygen, hydrogen, nitrogen. Just 2 types of. And second pair, it's a cytosine guanine. That's mean if in one chain there will be cytosine, second one chain formed such way in front of it guanine present. So, and if there will be something wrong in lactin-lactam tautomerism and in first chain lactin form appears, the secondary structure can't be formed properly or can't be formed at all. So take a look for guanine and cytosine. There are 3 hydrogen bonds stabilizing this secondary structure because of them. And it's a hydrogen-oxygen, 2 hydrogen-oxygen bonds, and 1 hydrogen-nitrogen bond. 3 of them. To illustrate, if you have to illustrate a complementary principle in this cycle, in this bioorganic chemistry first year, you need to just mention what is that this, according to this principle, secondary structure of DNA RNA is stabilized. Hydrogen bonds stabilizing these structures, and there are 2 base pairs. You should name them and draw formation of the hydrogen bond same way as I told you to draw just now. Not necessary to draw both chains, and it takes time enough to explain the idea of formation of hydrogen bond, enough to show that they are bonded to the sugar and polynucleotide chain, these nitrogenous bases. For secondary structure, take a look here, illustrated more exact how this secondary structure of nucleic acid looks like. So phosphodiester bonds stabilizing the structure, primary structure of nucleic acid, as it's not a sulfur, as it's a sugar. So polynucleotide chain, here right side nitrogenous bases, aromatic nature, and the secondary structure formed exact way. If here cytosine, here will be guanine, thymine, adenine, adenine, thymine, 3 or 2 hydrogen bonds. So RNA, there are 3 types of. It's a messenger, ribosomal, and transfer. They look different, and all of them participate in a protein synthesis. But secondary structure of RNA, it's not a double helix form for human. It's a clover leaf, stabilized by intermolecular hydrogen bonds according to the same principle. But because of RNA consists much higher number of minor nitrogenous bases, there can be different pairs also present. So intermolecular hydrogen bond. So that's why clover leaf. It's a secondary structure. Possible to find tertiary structure for these compounds, but it's up to our cycle. So biological function, DNA, it's a source of genetic information. RNA read this information from and bring transport amino acid to form according to the exact nature, and then protein synthesis occurs. No, it's for simple just. So one of the very important questions you should know how to answer, it's a hydrolysis of ATP, one of the important nucleotides. We deal themselves not as a structural part of nucleic acids. So ATP hydrolysis. ATP, it's an adenosine 5-triphosphate. Why once 5? Because of it once all these triphosphate once bonded to the sugar, 5th position. So for shorter ATP, or we can write 5 apostrophes ATP, but usually it's no need. ATP, when it's written, we already understand that it's their 5th position once. So what's happened here due to addition of water? When hydrolysis happens, it's not just addition of water, it's biochemical process. So plus water, it's losing, water destroyed ester bond. As a result, phosphoric acid released, usually is the form of salt because of its in alkaline medium happen in our body 7.4. So phosphoric acid lost. As a result, their formation of diphosphate appears. Here it's essential to indicate fifth position once. Why? Because of diphosphate can be 3,5 diphosphate. One phosphate fifth position, one phosphate third position. Such diphosphate are present in nature and they are formed due to partial hydrolysis of nucleic acids. So here diphosphate bonded once and some heat released. Now approximately 30 kilojoule per mole energy for both and one. No, a little but difference. So, but it's still ester bond present. That's why plus one molecules of water, still hydrolysis appears with releasing of one more phosphoric acid and some value of heat. This heat goes in some important biochemical processes, no, for example, sodium-potassium pump. So, this is hydrolysis. No, necessary to add here water to understand that the water adds. As a result, we have AMP participate then formation of RNA synthesis. Hydrolysis not happen itself. They are complex with magnesium formed, no, but the scheme, the idea of this reaction is present here. According to the biochemical importance, the text, I will just mention their structure without any biochemical explanation because of, no, it's upper of this lecture. It's will be given in your informative block for preparation for class, and as well as this information more exact you will study next year in biochemistry, even biochemical transformation of every vitamin. Now the task to understand classification and difference in structure from biochemical point of view. No, we will not insist you memorize the structure, but you should know at least how they looks like to recognize exact vitamin when their few are present. So what are vitamins? They are organic compounds that are necessary to maintain normal health, growth and nutrition. That's why problems with vitamin metabolism, deficiency of vitamins leads to serious problems in health and even death. So all vitamins can be classified into two groups: water-soluble vitamins and fat-soluble vitamins. Due to this, there are different prescription. So water-soluble vitamins can be classified two groups. It's B-complex, the biggest part, and non-B-complex. Among non-B-complex, you need to know vitamin C. B-complex, energy releasing, B1, B2, B3, and biotin I mentioned as a sulfur-containing ring, 5-membered as you remember. Hematopoietic, that means participate in blood formation. It's a vitamin B12. As you remember, I hope when we pass complex compound, they consist cobalt and same unit porphyrin as it was present in hemoglobin. So it's a complex compound, and deficiency of cobalt as well as deficiency of all vitamin B12 leads to anemia, the cancer one. And folic acid, here also it's a B complex. Among other B complexes, it's vitamin B6. Fat-soluble vitamins, A, D, K, A. So, some information, some structural, biochemically important vitamins. They are vitamin B1, thiamine. So for you to just to understand, to hear this word once, the deficiency of this vitamin leads to beriberi disease. So as you see, here we have two cycles in a structure, heterocyclic compounds. It's a thiazole and pyrimidine. but they are bonded not condensed way, they are bonded isolated way. That's why each one has own numbering. Vitamin B2, riboflavin, it condensed cycle. As you see here, present two different nitrogen containing rings, and this is aromatic compound. So vitamin B2 deficiency, one of the symptoms, it's quite interesting, leads to the night blindness. That's why some students think that night blindness is only vitamin A deficiency, but it's not only. Among water-soluble vitamins, B6, it's a pyridine containing, and vitamin C, BC, it's a folic acid. As you see, quite hard structure to draw, but easy to recognize. And vitamin B12, cyanocobalamin, as you see, consists cobalt as a central metal atom, cobalt 2 positive. Ascorbic acid, vitamin C, potentially fatal disease, leads to, deficiency of vitamin C leads to potentially fatal disease, scurvy. And vitamin PP, nicotinamide, niacin, deficiency leads to pellagra. 3D disease. 3D because of diarrhea, dermatitis, and dementia. Now, vitamin D, everyone knows, together with the calcium, participate in formation of normal structure of bones formation, and that's why deficiency of vitamin D for kids it's a ricket, and for adults it's osteoporosis, osteomalacia. Vitamin D can be different. Vitamin D2 structure present here. Now, it's also interesting because of some who pass lipids topic already can recognize the structural unit and should understand that vitamin D also somehow depends on metabolism of cholesterol. Now, from fat soluble there are a few structures. It's vitamin A, retinol, as you remember, it's one of carotenoids. From carotenoids appears and leads to night blindness. It's one of the symptoms more often students knows. Alpha tocopherol, vitamin E, and vitamin K, K2 in this case, it's a methionine. I think that's it. So no, for today's topic it's enough. It was hard to understand all of this. To understand, not hard, hard to draw. That's why, as you should know how to draw dinucleotides, how to explain formation of the secondary structure of DNA, RNA. Now, for vitamins, you don't need to draw these vitamins, but there are a lot of MCQ questions to recognize the structure. And deficiency diseases, it was possible to find in appendix page, informative block. But heterocyclic compounds themselves, necessary to memorize, as they are structural unit of all of these biochemically important compounds. No, it's a hard work, and it's only one way to memorize them. It's a draw again and again. Next time will be not so many, but also a lot. Proteins also, to draw any tripeptide or structural part of protein primary structure, necessary to memorize 20 amino acids. 20 by heart. You need to draw any of them when teacher asks. It's a first step to be ready for next year biochemistry, when you will start in September with a proteins topic, where amino acids you need to know classification and structure. Well, about them we will talk about next week. So one more thing about attendance. I'm very disappointed first division attendance. We should start 8 o'clock because of it's a first lecture. That's why connection always 5 minutes later. I don't know why. We always starts 5 minutes, 5 after 8, but 8 a.m. according to Moscow time, you should be ready to join to the conversation. What happened again today, it's unacceptable because of some students added much later, almost the half of lecture passed. Told you, right? It's a disrespect. And I know that in India, 2 hours and a half difference in time. That's why they are 10:30 already. And it's not too early morning. It's necessary to wake up on your computer and to say good morning where there are so many minutes past. No, I don't know. I can see everyone that's here. Okay, so 201 group. Don't forget, we have this topic today, and I hope you're ready to draw all of these structures. Unfortunate you. All other, see you next week. My group, don't forget, 2:40 and not 1:50 we have class. 2:40. 40 minutes past 2, okay. Okay, so lecture is over. It's a short because of I can just show you this formula, unfortunately, and I'm sure 100% that you didn't draw this or just listen. No, some dinucleotides really it's hard to draw, but at least 5-member twin. I hope information it was used properly. Okay, goodbye. See you next week.